Today we study about electromagnetic waves in electricity and magnetism. James Clerk Maxwell urged that this was indeed the case, not only an electric current but also a time-varying electric field generates magnetic field. While applying the Ampere circuit law to find magnetic field at a point outside a capacitor connected to a time-varying current, Maxwell noticed an inconsistency in the Ampere circuit law. He suggested the existence of an additional current called by him the displacement current. To remove this inconsistency, Maxwell formulated a set of equations involving electric and magnetic fields and their sources, the charge and current density. These equations are known as Maxwell's equations. Together with Lorentz force formula, they mathematically express all the basic laws of electromagnetism. The most important prediction to emerge from Maxwell's equations is the existence of electromagnetic waves, which are time-varying electric and magnetic fields that propagate in space. The speed of the waves, according to these equations, turn out to be very close to the speed of light, obtained from optical measurements. This led to the remarkable conclusion that light is an electromagnetic wave. Maxwell's work thus unified the domain of electricity, magnetism, and light displacement current. Maxwell showed that for logical consistency, a changing electric field must produce a magnetic field. This effect is of great importance because it explains the existence of radio waves, gamma rays, and visible light, as well as all other forms of electromagnetic waves. To see how a changing electric field gives rise to a magnetic field, let us consider the process of charging of a capacitor and apply Ampere circuit law given by closed integral b dot dl brought mu naught I. To find magnetic field at a point outside the capacitor, figure 1 shows a parallel plate capacitor C, which is a part of circuit through which a time-dependent circuit flows. Let us find the magnetic field at points such as P in a region outside the parallel plate capacitor. For this, we consider a plane circular of radius r whose plane is perpendicular to the direction of current carrying wire and which is centered symmetrically with respect to the wire. From symmetry, the magnetic field is directed along the circumference of the circular loop and is the same in magnitude at all points on the loop, so that if B is the magnitude of the field, the left side is B 2 pi r. So B 2 pi r over mu naught I. Since the contradiction arises from our use of Ampere circuit law, this law must be missing something. The missing term must be such that one gets the same magnetic field at point P, no matter what surface is used. If the plates of a capacitor have an area E and a total change Q, the magnitude of the electric field E between the plate is Q by A, what I have shown. The field is perpendicular to the surface S it has the same magnitude over the area A of the capacitor plates and vanishes outside it. So that is the electric flux phi through the surface. Through the surface phi using Gauss law, it is phi E बराबर E into A बराबर 1 of solar naught Q by A into A बराबर Q बटा solar naught. Now if the charge Q on the capacitor plate changes with time, there is a current I बराबर dQ by dt. So dQ E by d phi E by dt बराबर d by dt Q by epsilon naught बराबर 1 epsilon naught dQ by dt. This implies that for consistency epsilon naught d phi E by dt बराबर I. This is the Missing term in Ampere circuit law. The current carried by conductors due to flow of charges is called conduction current. The current due to changing electric field or displacement is called displacement current or Maxwell displacement current. The total current I is the sum of the conduction current denoted by IE and the displacement current denoted by ID. बराबर epsilon naught d phi E by dt. So I बराबर IC plus ID है ना, IC plus ID बराबर IC plus epsilon naught d phi E by dt. Closed integral B dot dl बराबर mu naught IC plus epsilon naught d phi E by dt, known as Ampere's Maxwell law. There is only a displacement current due to time varying electric field. Maxwell equations closed integral E dot dA बराबर Q बटा epsilon naught बराबर phi. Closed integral B dot dA बराबर 0. Closed integral E dot dl बराबर minus d phi V by dt. And closed integral B dot dl बराबर mu naught I C plus mu naught epsilon naught d phi E by dt. Nature of electromagnetic waves as shown in the figure. B and E are perpendicular in this case. The electric field is along Ex is along X section, varies sinusoidally with Z at a given time. The magnetic field by By is along the Y axis and again varies sinusoidally with Z. The electric and magnetic field Ex and By are perpendicular to each other, and to the direction Z of the propagation we can write Bx and By as follows. Ex बराबर E naught sin kz minus omega t. By बराबर B naught sin kz minus omega t. Here k is related to the wave length lambda of the wave by the usual equation k बराबर 2 pi by lambda, and omega is the angular frequency, k is the magnitude of the wave vector or propagation vector k, and its direction describes the direction of propagation of the wave. The speed of the propagation of wave is omega by k, omega बराबर c k, where c बराबर 1 by root over mu naught epsilon naught, nu बराबर 1 omega by 2 pi, lambda बराबर 2 pi by k, 2 pi nu बराबर c 2 pi by lambda और nu lambda बराबर c, Bv बराबर epsilon naught by c. Thus the velocity of electromagnetic waves in free space or vacuum is an important fundamental constant. Electrical energy density बराबर 2 by 2 epsilon naught E square. Magnetic energy density बराबर 1 by 2 B square by mu naught.